Good morning, everyone. Welcome back. Today will be lecture 7, but before I get to that, I wanted to make a quick announcement. Yeah, that was my bad. Today's quiz 4, well, at the time of this recording, it was quiz 4. Um, there were some issues. A student, one of your classmates, actually brought to my attention that there were questions on the quiz that were not supposed to be on the quiz at all. So there were 4 questions on the quiz. 7 through 10 that were about cyclohexanes and the relative stabilities of cyclohexanes, and we hadn't covered that yet. That quiz 4 was only supposed to cover lecture 5, and that definitely were questions from a different lecture, lecture 6. So I apologize for that mistake. To rectify the situation, I was going. We're going so fast, I just can't remember what we covered in every single lecture when I write these quizzes. So, but my mistake is your gain because since there are 4 questions there that were not supposed to be in the quiz, I've decided that I'm just going to give everybody 40 points on quiz 4. So it doesn't matter if you got it right or you got it wrong when you did the quiz. Regardless, you'll get 40 extra points on the quiz. So that's how we'll take care of that. And expect those questions again or something like them again on the next quiz or something like that, right? So that's how we'll fix that problem there. Again, I apologize for that little confusion. I'm sure you were very confused yourself when you encountered those questions during the quiz. So, sorry. Anyway, let's go ahead and start lecture 5. And lecture 5, sorry, not lecture 5, lecture 7. Lecture 7 is a continuation of stereoisomers. And let me switch this view real quick. This is going to be a particularly long lecture, but we need to finish stereoisomerism, start reactivity next week, right? So before we even do that, though, let me just continue on my corrections to mistakes I made this week. So this was from lecture, also from lecture 5, I believe, about alkanes, and I incorrectly stated that the longest carbon chain or the parent chain is this chain right here. That's wrong. Actually, it's actually going to be this chain right here. Right? Both of them have 7 carbons in the chain, right? So they actually tie in the number. For some reason, I miscounted and thought that one had 6 or something like that. And so the way you tell the difference, though, is that the second rule says that the one with the most constituents would be the one that would be the parent chain. And so for this guy, if you had this one as your parent chain, right, there would only be 2 substituents. This one right here and this one right here, right? But if you were to do this one as your parent chain, you'd have 3 substituents. This ethyl group here, that methyl group, and that methyl group. So that's clearly the parent chain there. My bad, miscounted, hard of math. But let's keep going. So what are we talking about today? Oops, went too far, right? So today we're going to be talking about R and S configurations, and these happen to deal with enantiomers, right? So enantiomers are different compounds, right? So they do not have identical names, right? They must not have identical names, right? And we talked about this in the previous slide, or not previous slide, but previous lecture. What enantiomers are? They're the right-sided and the left-sided version of a stereoisomer, right? Of a stereoisomer. And so they have opposite configuration at their chiral centers, right? And so we have to use a system called the Kahn-Ingold Prelog system, right, to designate either R or S configuration. Okay, and so there's a whole set of rules that we'll go through in just a second, right? But if a compound has an R configuration at its chiral center, then its enantiomer will be the S configuration. Okay, so just before we even go any further, right, you can see that these are enantiomers of each other, right? One is R, one is S. We'll figure out which is which in a second, right? But notice that the only difference between the two is that in one of them the chlorine is coming towards you, and the other one the chlorine is going towards the back of the paper, right? And so the R configuration will be the enantiomer of the S configuration, and then vice versa. The S configuration will be the enantiomer of the R configuration. Okay. So here are the steps, just real quickly before we go through each one independently in more detail. R and S is assigned to the chiral center using a stepwise procedure. We use the atomic number to prioritize the 4 groups attached to the chiral center: 1, 2, 3, and 4. Right, and so we do that based on the atomic number of the attached constituent. So the highest the highest constituent in atomic number, right, atom in atomic number will be the highest priority, and that would be labeled 1. Excuse me, and then second will be second, number 2, and so on. Then you arrange the molecule so in space so that the lowest priority group faces away from you. Most commonly, that is going to be a hydrogen, right? But there could be other constituents. Then you count the group in its priorities. Count the group's priorities by count the group priorities 1, 2, 3, and 4, right, to determine whether or not it's a clockwise or counterclockwise direction. If you're counting it in the clockwise direction of 1, 2, 3, and 4 around in that circle, are a clockwise direction, then it's R, and then if it's a counterclockwise, then it's S, right? And this is one of those times when having a handheld model would be awesome, okay? Because seeing it in picture form is actually a little difficult. At least it is for me. I can visualize things in 3D way better than I can see them when they're flat on a piece of paper. So here we go. Let's start with this particular molecule here. Here's step 1. We're using the atomic numbers to prioritize the 4 groups that are attached to the chiral center, right? We know that this is the chiral center because this carbon right here has the wedge and the dashed wedge, right? The solid wedge and the dashed wedge, right? And so that's definitely a chiral center because you can have the chlorine and the hydrogen switch positions such that the hydrogen is no longer pointed at you, it's pointing to the paper, and then the chlorine is pointed towards you, right? So that's definitely a chiral center. Thus, it has an R and S configuration, okay? So I've actually built this molecule here for you, and it's going to be really difficult for me to do this because as I'm seeing it in the front, it's backwards from the way that you see it in the camera. But we'll do our best. Just to make things easier, the chiral center here, the carbon is blue, right? All the other carbons are normal because they're not the chiral center, but the chiral carbon here is blue, okay? So if I'm looking at this here, let me see if I can make this half size so that you can see it better. Well, that's not good because it blocks the molecule. Maybe I can actually move this up a little bit and to the left. There we go. That looks good. Okay, so the first thing we have to do is prioritize our atoms that are attached to the chiral center. Okay, so this is the molecule here. I built it for you. Okay, and I want to make it so it looks like what it looks like on the paper for you. So I think I might have already done it. Let's see here. No, I haven't. Yes, I have actually. See? So here's the chiral center. Okay. The blue right here in the center is the chiral center. Right there. Okay. The chlorine is the green. It's coming back, right? And then the hydrogen right there is going forward. And then the ethyl group is going to the right. Okay. Oh, sorry. The ethyl group is going to the left. And when I'm looking at it, it's going to the right. But in your perspective, it's going to the left. And then the oxygen and its group is going to the right. Okay. There we go. So that's what that looks like. So the first step is to actually prioritize the different constituents, right? So our different constituents here are the hydrogen, the chlorine, the oxygen, and the carbon. And you prioritize based on the atomic number, right? And the highest atomic number here is this chlorine here in the back. So that gets 1. After the chlorine is oxygen, that gets 2. Oops, that's oxygen over here, sorry. Oxygen, that gets 2. Okay. After that is carbon, that gets 3. And then the hydrogen here gets 4 because it's the lowest priority. Okay? So now that we have those labeled, right? 1, 2, 3, and 4. 1, 2, 3, and 4. Right? Let's go to the next step. You want to arrange the molecules so that the lowest priority is going behind you, right? It's going behind you. And so right now the lowest priority lowest priority constituent is the hydrogen, and it's pointing right at you, right? So all you have to do is turn it this way, like that. And now the highest priority is turning towards you, and the lowest priority is pointed backwards. That's what we need to do, okay? Just rotate it, okay? And now that's what it should look like, okay? Let's go to the next one, next step. Now we want to count the priorities in order, all right? And when we count them, 1, 2, 3, and 4, if we're counting in a clockwise direction, then it's R. If it's in counterclockwise, it's S, right? So let's count this here. Here's 1, okay? I'm going to have to look at it like this so I can see what direction I'm going. Here's 1, okay? 2, right? 3, 4, right? 1, 2, 3. Yes. It's hard to see when I'm like doing that way. So 1, 2, 3, 4. And so I'm going to do it so I can look at it from the front. 1, 2, 3, 4, right? Which means that right there is going to be counterclockwise, right? So if it's counterclockwise, as you can see here, right? Definitely counterclockwise. This is going to be an S. Okay, that's going to be an S. So if we were to remember what I said in the previous slide, if we were to just flip these, then it would be it's an anomer, and then that would be the R, an anomer, right? But as is, the way it's built right now, this molecule is S, right? Because we're counting counterclockwise. Okay? Good stuff, good stuff. Next. Okay, I can put that down. Okay. And I'm going to go ahead and fix my view. So I'm back to half and half here. And then switch back to presentation view. Okay. Ooh, I need a drink after that one. That was a lot of gymnastics. Acrobatics, okay? Okay. So designating R and S continued, right? We have some challenges here. And one of the challenges is if you have the two of the molecules or substituents connected to the chiral carbon, right, are the same. So here we have a carbon and we have a carbon, okay? And they're the exact same, right? They're both CH2s. They tie, right? Carbon to carbon. Then CH2s, 2 H's each, right? So the way we do a tiebreaker is you would put the substituent atom at the top in a list, and then the things connected to it under it, right? And so in this case, they're both CH2s, right? They're both CH2s. And so everything connected to it is also the same too, right? 2 H's each. So we can't use this to label priority. So what do? We go to the next one after that, the constituent. And now, when we do it, right, we still have two carbons here that are the same. But this carbon over here has a methyl group attached to it. And this carbon over here has 2 H's attached to it, right? 2 methyl groups, 2 H's. Okay? So we can do our tiebreaker again, tie-breaking procedure, where the first thing is always the constituent itself. They're both carbons, right? Right there and right there, they're both carbons. But then the next one after that is the methyl group. So they have you have a carbon there on the second atom from the constituent, but over here the second atom from this constituent is a hydrogen, right? So in this little tiebreaker, carbon wins because it has the highest atomic number, so it gets higher priority over. It gets higher priority over the other alkyl chain on this side, right? And so now we can easily label, the oxygen as being the highest priority because it's the highest atomic number. Okay. Then, and then 2 is over here, right? 2 is over here because that carbon is the next highest priority. And then 3 would be the next hydrogen, would be the next priority over here. And then 4, see, normally hydrogens are always, when a hydrogen is directly connected to a chiral center, it's always in the 4th priority, right? So that's how you would do it if you had atoms that were connected to the chiral carbon that were identical. You'd have to go to the next layer of carbons, okay? And again, that's super confusing, I know, but it's a lot easier if you have a molecular model kit. You can try it out, okay? So you can see it for yourself. So here's another example, right, of what we just did in the last slide. Again, 4 here because hydrogen is always the lowest priority, and then we already know that oxygen is 1, right, because it's the highest priority with the highest atomic number, right? The priority is based on the first point of difference, right, when you do the second layer. Here we have a CH2 again. We have 2 methyl groups again, right, on the other side. So this time, though, right, there is an OH attached to that CH2, not just another carbon, right? And over here we still have a methyl group. So remember in the previous one, it was 2 carbons that were attached to. There were 2 carbons, and then one had methyl groups coming off of it, and the other one had hydrogens coming off of it. But this time we have a carbon that has methyl groups coming into it. But this time, in this one over here, it has it has 2 hydrogens, but it also has an oxygen, right? So this time it's a little different because when you go to the second layer, oxygen is actually in there, and it immediately tie breaks. All right, with that carbon that's there. Right, that carbon of one of the substituents second layer, right? Remember over here, okay? Over here we had 2 carbons. Then we had to go to the second layer for the second layer there for the second attached atom to do the tiebreaker, carbon versus hydrogen. But over here, right, it was just the first attached, because oxygen clearly outweighs carbon when it comes to periodic mass, atomic mass, right? So we can easily, again, label oxygen here because it's the one that's the main constituent, and then 2 here for this carbon because it has an oxygen attached to it, 3 here because it has a carbon attached to it, and then 4. Okay? 4. And you may be asking yourself, I just thought about this. You may be asking yourself, how do I count this when it's like 1 in one corner and 2 in the other corner, and then 3 in one corner and 4 in the other corner? Like it's like crisscross and stuff, right? How do you make that a clockwise or counterclockwise or pattern? Well, you still have to remember that you will need to rotate it so that the hydrogen is pointing backwards. And once you do that, then you'll have it so that you can actually count it in order, in a circle, instead of crisscrossing like this, That's definitely neither clockwise or counterclockwise. All right, so what do we do when we have double bonds? When prioritizing for the Kahn-Ingold and pre-log system, double bonds count as two single bonds. So, in this case, that's two single bonds, right? And so oxygen is just counted twice. Oxygen is just counted twice. Okay? So when you're trying to figure out between the carbon over here, right, and this carbon over here, right, this is another carbon over here, that's a methyl group right there, right, and then this carbon over here, the oxygen actually gets like the priority here because all those carbons are less atomic weight than the oxygen, right? And so no matter what happens over here, you can go through that priority later with the list of its attached things. But this carbon here will get the priority because it's got oxygens attached to it. And it has the highest priority, highest atomic number. So you would start out by saying that this is number 1 right here. Okay? So I kind of alluded to this in a previous slide, but if you had a handheld molecular model, it can be very useful in arranging the molecules in space at the lowest priority so that the group faces away from you, right? So here's a trick. If you switch the two groups on the chiral center, it will produce the opposite configuration, which I told you that before, right? When we were looking at this guy right here, right, we had it in S configuration right now. If I pop this off and pop this off like this, we've just changed it to its R configuration, right? We've just changed it to its R configuration because this time we have to rotate this thing around again, like this, okay? So that the H is coming back at you, okay? And now you count the priorities. 1, 2, 3, 4. Now you're going clockwise. So that's R configuration, okay? Good stuff, good stuff. So here's just a summary of the steps for assigning priorities and assigning RS configuration using the Kahn-Ingold pre-log rules. Right. The first step is to identify the 4 items directly attached to the chiral center, and of course the chiral center is always the one that has the dashes and the wedges on them. Right. Step 2 is assign the priority to each atom based on the atomic number. The highest atomic number receives priority 1, the lowest atomic number receives priority 4. Most commonly, that number 4 is going to be a hydrogen, okay? And then step 3, if 2 atoms have the same atomic number, right, move from the chiral center to the next one, right? And you're looking for the point of difference as you keep on going from layer to layer, right? And then once you get to the something that's different from each other, right, then you assign the priority based on which one has the highest atomic number there, right? So say the first two constituents, the first two constituents you had that was connected to the chiral carbon were 2 other carbons, right? So you would go to the next one after that, right? The next atom after that. If the next atom after that, one carbon had an oxygen connected to it and the other carbon had a carbon connected to it, then the one with the oxygen will get the priority. Okay? Step 4, rotate the molecule so that the the lowest priority group is pointed back towards you, and then you count the number of priority, 1, 2, 3, and 4, and if you're counting them, and it goes in a clockwise direction, your R, and if you're going in the counterclockwise direction, I can't tell. It's because I'm seeing a mirror image of myself in the camera. So, if you're going a clockwise direction, right, then you're an R, and if you are going counterclockwise direction when you're counting the priorities, then you're an S. Okay. All right. So skill builder here. Assign the configuration to this compound. Okay. Assign the configuration to this compound. Skill builder. Oh, that also means too. What does that mean? skilled builder means that there's going to be example videos in Wiley Plus. So check out the Wiley Plus because it's going to help you out with this, right? It's going to help you out with this. Okay, so the first thing I'm going to do here is just to indicate that I do have hydrogens here. Okay, I do have hydrogens. Right, okay, so our chiral center is this right here. This is our chiral center, okay? So the groups that we need to compare are a hydrogen that's here, and right now, this NH group, this amine group right here, is pointed back towards you, right? No, sorry, back towards the piece of paper, which means that the hydrogen is coming out this way, okay? All right. So it's already pretty easy now to do the priorities, the first level of priority, right? Because when you look at this nitrogen versus this carbon, and this hydrogen, right? You already know then that the number one here will be the nitrogen, because the nitrogen has the highest priority, highest atomic number, higher than carbon. Then over here, you already know that the hydrogen has the lowest priority, so you can name it 4. Name it 4. You can label it 4, right? Label it 4. So now the question is, which of these two has the highest priority? This carbon or this carbon? And you can easily tell from this particular example because those two carbons are the same, but if you go to the next layer or the next atom after it, right? For this carbon, the next atom after it is an H, okay? And for this carbon, the next atom after it is an oxygen. So what's going to get the priority here? The priority is going to be this one. So we're going to go 2 here for that carbon, right? Maybe I should write it closer to 2 because then it looks like I'm putting on the oxygen. 2 here for that carbon and 3 here for that carbon. Okay? So, oh look, we can already count this here, right? No, we can't. What's the next step? What's the next step? You got to rotate it, right? So that the hydrogen is pointed backwards. Okay? And so with the hydrogen pointed backwards towards you, so that would make it, you would flip it, right? And I'm just going to draw the part that we care about here. So I'm going to cut it off right there. And that's probably good enough. So this part is flat, okay? And then this is the squiggly line over here, okay? And then where the diphenols here, right? And then now my hydrogen is going backwards. And then, oops, I did that wrong. Hold on a second. There we go. Solid wedge there for NH2. And then hydrogen going backwards, right? And then over here was the carboxylate, I believe. Yes. Right there. Yes. Okay. Flipped it around. Okay. So now remember this is 1. Okay. This is I forgot which ones which are. This is 2. Okay. This was the third one, right? Yeah, this was the third one. And this was 4. Okay? And that's actually really hard to tell what the order is. So I'm going to build this, right? Because right now it looks like it's zigzagged. And I'm going to build this so that you can see on the 3D model, right, what it is, okay? So we have then, here's the oxygen right here, okay? The oxygen is the red one. And then let's say that the green one, so that's flat, right? The green one is the nitrogen right there, okay? And then we have the CH2. There's more connected to the CH2, but don't worry about that. Okay, so right? So now the highest priority is pointed out to you, towards you, okay? And then the lowest priority is going backwards now, just like it is in the picture, right? Actually, it's like this. It's upside down, like this, right? Oxygen is over here, okay? Actually, it's a carbon connected to an oxygen. I should probably make that accurate. Okay, there we go. All right, so chlorine is coming out, not chlorine, sorry, nitrogen coming out to you, hydrogen going backwards, okay? Oxygen with the carbon with the oxygen is over here, okay? Which I think it looks exactly the way it looks in your this, I can't tell. It's actually backwards because it's the mirror image. So for you, it would look like this. Mirrors are so confusing. Yeah, so that is what it would look like for you. Okay, that's what it would look like for you. I can't use me looking at the model. I have to see what it is in the see what it looks like in the camera, so that doesn't confuse you. And then let me just make it bigger here so you can see. Right. There we go. So nitrogen right here, right, is nitrogen here, coming right out at you. Hydrogen back here. It's back here. I'm holding it in the back right there, right? And then oxygen connected to the carbon up here, and the CH2 group. Okay. There we go. And now I'll count it on the screen so it makes more sense to you, right? So you're going, here we go. You're going chlorine, right? You're going chlorine, carbon with the oxygen, right? So that's 1, 2, okay. 1, 2. We're going 1, 2, and then this carbon here, and then this hydrogen back here. So 1, 2, 3, 4. Okay. So 1, 2, 3, 4. That's a counterclockwise. So this is a S molecule. Okay, that's an S. Okay. Let me tell you, it's kind of difficult having to do this in a camera. So, yeah. I'm going to count on the screen here. You can't see me counting because I'm counting on the screen. 1, 2, 3, 4. That's definitely counterclockwise. Yeah. Okay. All right, that was a little rough. And then I'll switch back to presentation view there, right? So it would be, if we're doing that, it's 1, 2, 3, and then 4, the guy in the back, right? And this guy in the back here, I guess it was a little confusing because I have it pointed upwards here, but it didn't have to be pointed backwards or up like that. It could have been over here too. It would have been the same as if it was over there, right? And then you still could have gone 1, 2, 3, 4, and that would have been also S configuration because you're going counterclockwise. Okay. In fact, let me draw that again just so that you can see it very clearly here. I flipped it around like so. Okay. Here's the carboxylate over here, or the carboxylic acid. The NH2 is pointed downwards here. Okay. Right. And then we have our CH2, and then we have like the rest of the molecule here, the benzene ring, that doesn't really matter. Okay. So in this picture over here, I drew it so that it was pointed upwards, but the hydrogen was still going backwards, right? Which is right, but you could still also do it this way too. Like that. Still means the same thing, right? Still means the same thing, going back towards the back of the page, right? And now you can more clearly see 1, right, for that one. For this carbon right here, it's 2 because it's got the oxygen connected to it. For this carbon here, it's 3 because it has hydrogens connected to it. And then you have 4. So 1, 2, 3, 4. And that's counterclockwise. So that is an S configuration. Okay? IUPAC, our International Union of Pure Chemists, Pure and Applied Chemists, right? They have designated the R and S configuration to be used in the IUPAC name to distinguish enantiomers, right? So this is R-butanol and this is S-butanol, right? R-butanol and S-butanol. This here is interesting because you have a chiral center there, and you have a chiral center here, so 2 chiral centers. So you have to designate whether it's R or S for both, okay? And so in this case, we have the 2R, right, which is the pentanol part because it's a 5-carbon, makes it a pentane, and you name all alcohols that are connected to alkanes pentanol, right? And it's at the second carbon, right? And it's R. That's why it's 2R. And then the methyl group is the third on the third carbon, right? And it's an S. It's an S. Okay? It's an S. Whew, okay. That was rough. Why don't we try it with this one? Let's confirm that this is actually an R right here, okay? I will go ahead and draw in the hydrogen here. Remember, this hydrogen can go in any direction, but as long as it's going to the back, right? Because if you're looking at it in three-dimensional space, you can tilt it, right? And the hydrogen could be pointed upwards but back, downward to back, but to the left but back. But as long as it's in the back, it's fine. And you can point it so that it fits in your 1, 2, 3, 4 count, okay? So top priority here will be the oxygen. So that's number 1. 4 is the lowest priority for hydrogen, right? And then we have a carbon with a hydrogen connected to it and a carbon with another carbon connected to it. So what's going to be next after that? This will be 2, okay? This will be 3, because a carbon connected to another carbon is higher priority than a carbon connected to a hydrogen, right? So we can count, right? 1, 2, 3. And again, this hydrogen back here that's pointed backwards, I mean, I didn't have to put it over there. It would be the same thing if it were over here, right? So that's 4. Okay, that's clockwise direction. That makes it an R. Okay, that makes it an R. Okay, good stuff, good stuff. Let's confirm that this is then a S-butanol, 2-butanol then, right? Again, there's a missing hydrogen, so I'll go ahead and draw on the hydrogen, but know that it's fluid because as long as it's pointed towards the direction it's the wedge is showing, it could be up, right, whatever, right? Because as you're looking at it 3D wise, it really depends on which perspective you're looking at it from. As long as it's in the back, it's good, right? Already we know that this is not in the back. This hydrogen is going to be in the front, right? So we have to flip it around. But the first step is not to flip it so that the hydrogen is in the back. The first step is to assign its priorities. So this is the same as the other molecule, right? One here. Then a carbon connected to a carbon is higher priority than a carbon that's connected to a hydrogen, right? All based on molecular formula, right? And then now the next step is to flip it around so that the hydrogen is in the back, right? So the flipped around molecule is going to look like this. Okay. No, not like that. Sorry. It's going to look like this, right? And then now the OH is facing towards you, okay? And then this is 2, this is 3, 1, 2, 3, right? And then the hydrogen, of course, is in the back here, okay? 4, 1, 2, 3, 4. Now you're going in the opposite direction of clockwise, which is counterclockwise, CC, right? CCW, where you watch shows like Vampire Diaries and the originals, CCW, right? Or is it just CW? Dang. I think I messed that up too. I think it's actually just CW. Comment below if if you're watching this on YouTube and let me know if it's CCW or CW. I can't remember now. The network. Anyway, counterclockwise means it's S, right? And clockwise means it's R. Okay. Whew, okay, so turns out though that enantiomers of each other, the S versions and R versions of each other, right? They're only differing because of their whether or not their chiral centers are pointing a certain substituent to the front or the back. Okay, but otherwise they're pretty much identical. Okay, and so they're not, sorry, I didn't mean to say identical, but they're identical in their physical properties. Okay, but enantiomers, though, do have differences in the way they interact with each other and other chiral compounds, and then they also differ in their optical activity, which we'll talk about in a second. But remember what I was talking about before with levocetirizine, which is Zizal, and cetirizine, which is Zyrtec, right? Levocetirizine, Zizal, doesn't make me sleepy, but Zyrtec does make me sleepy. And remember, those are two enantiomers of each other, right? So they have their substituent groups opposite of each other, right? So we'll figure that out in a second, which one's which. But that's what it means by how they interact with other chiral compounds. And a very good example of a chiral compound is like a protein or an enzyme, something in your body, right? They all are very, very, very chiral specific, right? So Carvone. I wonder what Carvone does. Anybody know? I don't know what Carvone is. So a little bit about electromagnetivity, right? So just so you know, light is also known as electromagnetic radiation, okay? And the colors of light you see is a part of the visible electromagnetic spectrum, okay? And the visible electromagnetic spectrum begins in the, I would say, 400s, where the indigos and blues are, right? And then, or purples. And then it goes all the way to where the reds are, right? Which is around the 600, 700 area, right? And so, but that being said, all electromagnetic radiation, light is electromagnetic radiation, right? But all electromagnetic radiation, including light, is composed of an electric field and a magnetic field, right? And that's why we call it electromagnetic radiation. So the thing to note here is that the electric field, if you have the direction of light going in this direction, it's pointed in this direction, right? The electric field will always be, right? The wave for an electric field will always be perpendicular to the magnetic field. Always be perpendicular to the magnetic field, right? Good stuff. Good stuff. A little bit of review of physics there, right? So why this is important is because enantiomers they have opposite configurations, where it's R versus S, of course, and rotate in plane polarized light, right? In opposite directions. Okay, they rotate in opposite directions, and we'll touch more on that here. To get light waves to travel in only one plane, light travels through a filter, right? And so when plane polarized light is passed through a sample of a chiral compound, the plane that the light travels on will rotate. Okay, so compounds that can rotate plane polarized light are optically active. Only chiral compounds are optically active. So only compounds that have a chiral center and can rotate based on the plane polarized light are optically active. So let's take a look at this picture right here. Okay, here we have light going in all kinds of directions. Okay, I mean it's going in all different directions. That's what that little asterisk looking thing is. Okay, but now we have a filter, right, where there's only spots where that are up and down, gaps where they're up and down. So the only thing that can pass through is the light that's going up and down, right, vertically. The one that was going diagonally can't go through. The one that was going horizontally can't go through. The one that was going another diagonally, the downwards, can't go through. When you have a filter that only has slits that are vertical, only vertical light can go through, right? And that vertical light can still pass through another filter, right, that also has vertical slits that it can pass through, gaps. And then your eye perceives that, right, as light, right, that is straight up and down, but you don't know that. It's just light to you. But imagine then that you had a light going all kinds of different directions, right, and you place a filter on it, and again it only had vertical gaps, so only vertical light could go through, right, like that. But then you put another filter after that, and now it only had horizontal gaps. Okay, if it only had horizontal gaps, then this vertical light here wouldn't be able to pass through, and you would not see any light at all, right? You would not see any light at all. And that's like the basis of like polarized sunglasses, how you can see certain shades, and I think I had a pair of sunglasses a while back that I lost because they were on a boat. I was on a boat and I was wearing these sunglasses, and they were super expensive. I think they were called Costa Mesas. Is that what they were called? Again, comment below if you're on YouTube and you can tell me. But they had like these polarized sunglasses, and when I was on a boat, it was really cool because I could look and see through the water and see things in the water, which is very convenient when you're trying to go fishing, right? And so, but one day, but if you had non-polarized sunglasses, they were just shaded, then you wouldn't be able to see through and see the little I mean, it wasn't clear if you were polarized, but you could still make out things under the water with polarized sunglasses as opposed to regular sunglasses. But then one day the boat was rocking, or maybe I was a little inebriated. Who knows? That's how you're on boats sometimes. And my sunglasses fell off my face into the water. I tried to jump into the water to retrieve my sunglasses. My friend stopped me, which is probably pretty good because we're out in the middle of Galveston Bay, and it's pretty deep out there at some points. So sad. Those glasses are so expensive. Anyway, next. So there's this thing called a polarimeter, right? And in a polarimeter, the plane of polarization of the emerging light is not the same as that of the polarized light, right? So what's happening here in a polarimeter is that, remember in the previous slide, if I had a vertical, filter, right, and only vertical light could pass through, but then I had a horizontal filter, then the vertical light stopped, right, because it couldn't pass through the horizontal filter. Okay, that's just having two filters. But then you could put something in between called the polarimeter tube, and even though you had vertical light coming through because of the filter before it, the polarimeter can change that light 90 degrees. So now that it's 90 degrees, it's now horizontal. It can it can pass through the horizontal filter, right? And you can see it now, right? You can see it now. As the arrows indicate, the optically active substance in solution in the tube is causing the plane polarized light to rotate, right? The plane polarized light to rotate. Cool stuff. So that's the essence then. The polarimeter, right? Polarimeter 2 has a molecule in there that's optically active, and it can change it. It can change the plane that the polarized light is going at, either vertical or horizontal. Good stuff. Whew, all right. There's some math here. I'm not going to make you do any math, but I'm going to briefly go through this. Don't expect any of this math on the test or the quiz. But enantiomers will rotate the plane of light to equal degrees but opposite directions, right? So the degree to which the light is rotated depends on the sample and the concentration of the path length of the light, okay? So a standard optical rotation measurements are taken with 1 gram of compound dissolved in 1 ml solution and the path length of 1 dm of light, right? Or I guess that would be 1 decimeter of light. Whew, okay. So let's consider then the enantiomers of 2-bromobutane, okay? We have R2-bromobutane here and S2-bromobutane here, right? Notice that the specific rotation for 2-bromobutane R2-bromobutane is negative 23, right, degrees. And then the S version is positive 23 degrees, okay? So just recall then that R and S refer to the configuration of the chiral center, but the plus and minus signs refer to the direction that the plane of light is being rotated, okay? So the point there is that the negative and positive don't have anything to do with the R and S. So, here we go. The reason why, by the way, the Zyrtec known as cetirizine, and then Zyrtec known as levocetirizine are named the way they are is because of this. Levorotary. Okay? A positive rotation is called dextrorotary. Okay? And then a negative rotation is called levorotary. Right? The compound below has an S configuration, right? But its optical rotation is levorotary at 20 degrees. But it's dextrorotary at 100 degrees Celsius, right? So 20 degrees Celsius is like room temperature. So its optical rotation is mostly levorotary, okay, which is negative. You can heat it up, and then it will go positive to dextrorotary, right? But again, there's no correlation between positive and negative and R and S, or dextrorotary / levorotary and R and S, okay? And so, optical activity, racemic mixtures. Quite simply, a racemic mixture is a mixture of 2 enantiomers, right? The magnitude and direction of optical rotation cannot be predicted and has to be measured experimentally. However, we can predict the rotation of racemic mixture to be 0 degrees. Why? It's because, well, a racemic mixture is 50% of 50/50% of 2 enantiomers, right? So if you have the 2 enantiomers, okay, and say it's the levocetirizine and the cetirizine from Zyrtec and Zyrtec, and you have a mixture of the 2 of them together, and it's a 50/50 mixture, right, of those 2 enantiomers, okay? Well, that's a racemic mixture. And when there's a racemic mixture, one cancels out the other, right? And so that's why the rotation of the racemic mixture will be 0. Okay? The rotation of the racemic mixture was 0. Meaning the rotation of the light that you pass through it, okay, will be 0. I don't know if I made that clear or not. When I was back here on this slide, right, I'm not talking about the actual molecule rotating, right? At room temperature, this molecule, right, will make light rotate towards the negative degrees, right? So that's why it's level rotary, the light that you pass through it. Not the molecule itself, but the light that passes through it, okay? But then at 100 degrees Celsius, it's going to be dextrorotary, right? Where it's a positive number of degrees, right? And that's the light is rotating 100, is rotating, okay? The positive direction instead of the negative direction, right? Make sense? Yeah. Just know that when we're talking about dextrorotary and level rotary, we're not talking about the molecule itself rotating. We're talking about it rotating light. Okay. All right. If one enantiomer is in excess relative to the other, then the mixture will have an optical rotation, but it will be less than the pure enantiomer, which makes sense, right? Again, if you had a 50-50 mixture of levocetirizine and cetirizine, Zizal and Zyrtec, right? There would be no rotation, right? It would be 0 because they cancel each other out. Like as a whole, they cancel each other out, okay? Because it's a 50-50 mixture. But if it's not a 50-50 mixture and you say you had more of the levocetirizine than you did, which is the Zizal, and less of the cetirizine, then you would have it a little bit more level rotary, right, of the light than you would otherwise have if it were a pure sample of levocetirizine on its own. Okay? So you can actually calculate this. You can calculate the enantiomeric excess, the EE. Literally, the enantiomeric excess is how much more of one enantiomer you have than the other, right? And you can do that based on how much the degrees rotates, right? And so here we have 2-bromobutane again, okay? And suppose that a mixture of R and S 2-bromobutane has a specific rotation of negative 4.6 degrees, right? That's a rotation of light, negative 4.6 degrees, right? It's not 0, so we know that there's a little bit more of one than the other, okay? This allows us to determine the enantiomeric excess, okay? So the percentage of enantiomeric excess is equal to the observed rotation, which is negative 4.6 degrees, divided by the rotation of a pure sample of the enantiomer, right, times 100. So that's negative 4.6 divided by negative 23.1 times 100%, and that means we have 20% more enantiomeric excess of the negative one, which is the level rotary one, right? The level rotary and level rotary enantiomer, right? Let me make sure. Yes, negative is level rotary. Practice the skill builder 5.5 on Wiley Plus, because I know that was a little confusing. It was a little confusing for me too, but I think I confused you and confused myself when I forgot to reiterate the fact that the molecule itself is not rotating. It is the light that passes through the molecule is rotating. Okay. So, in the end, we have some really, a summary of isomers here, right? We have isomers are actually separated into two different categories, of course. We have the constitutional isomers and the stereoisomers. Constitutional isomers, of course, are the ones with the same formula but completely different connectivity, right? But then we have stereoisomers. They are non-superimposable, okay, but they share the same connectivity. Those split up into two different categories: the enantiomers, right, which have non-superposable mirror images, right? So they have mirror images, but they're non-superimposable mirror images. But then we have the diastereomers, which are non-superimposable and they don't have mirror images of each other, right? Just a quick definition down here: stereoisomers that are mirror image, stereoisomers that are enantiomers, stereoisomers that are mirror images, right? And then diastereomers, they are the ones that have no mirror image at all. Okay. So a good example of a diastereomer is an alkene, right? And this is cis-2-butene and trans-2-butene, right? Methyl group is on the top. Both are on the top for the cis. They're on either side for the trans, right? And these are diastereomers. Okay? Because if you were to try to look at these in the mirror, they're not mirror images of each other, right? They are not mirror images of each other. Okay? They cannot be enantiomers because enantiomers are mirror images of each other. And since they're not enantiomers, they have different physical properties, right? Only enantiomers have identical physical properties. Diastereomers have different physical properties. Okay? Different physical properties. So these are diastereomers. So let's consider cyclohexane with 3 substituents here, right? There are 3 stereocenters, as you can see. This one, and this one, right? And so there are a total of 8 possible stereoisomers, right? Consider the relationship among them: the enantiomers versus the the enantiomers versus the diastereomers. Okay, diastereomers is a difficult word for me to say. So notice that these 8 stereoisomers are comprised of 4 pairs of enantiomers. So each of these, right here, they're already separated for you into the 4 enantiomers, 4 sets of enantiomers, right? Okay, 4 sets of enantiomers. These 8 stereoisomers are already separated for you into the 4 enantiomers. Okay, which makes sense because if you look at these guys, they are mirror images of each other, right? Whether they're superimposable or not, right? Sorry, they are mirror images of each other, but they are also non-superimposable, right? These here, right? The hydroxyl the hydroxyl alcohols means the same thing. The alcohol, methyl, and chlorine, right? Those are non-superimposable mirror images. These are non-superimposable mirror images. Those are non-superimposable mirror images. Those are non-superimposable mirror images. Okay? So what you can do is think of this as a family where you have 4 pairs of twins, right? And a total of 8 kids. Okay? Then each kid has 7 siblings where one of them is their twin, right? And the other 6 are all diastereomers. Okay? So what that means then is that this kid here, right, has 1 twin or 1 enantiomer, right? But all the rest of the family, right, the rest of these 6 kids here are their diastereomer brothers and sisters. Okay? And that's true of every single one of them. Okay? So let's take a look here at cholesterol. The number of possible stereoisomers for a compound depends on the number of chiral centers, N, in the compound. So the maximum number of stereoisomers is equal to 2N. Okay? So 2N right here. So what is the maximum number of possible stereoisomers or possible cholesterol isomers? Okay, well, remember what I said before. The chiral centers, right? We got to count the chiral centers, and they're the ones that always have the wedges on them. 1, 2, 3, 4, 5, 6, 7, 8. So 8 chiral centers. So that means 2 to the 8, right? And that is actually going to be 256, I believe. So the max number of isomers, right, that this molecule cholesterol can have is 256. And ironically enough, this is the most naturally occurring one of all the stereoisomers, right? That's the most naturally occurring one. Practice with Skill Builder 5.6 in determining the stereoisomeric relationships on Wiley Plus. Whew, okay. We're getting through this. We only got a few more slides. I'm just kidding. There's like 20 left. So symmetry and chirality now, okay? So any compound with one chiral center will be chiral, right? So that's a chiral center, again, is a carbon with 4 different substituents, right? Or different substituents on it, right? That makes it not symmetrical, right? So with more than one chiral center, a compound may not be a chiral compound if it has a plane of symmetry. Consider these 2 stereoisomers below, which possess 2 chiral centers. So what it's saying here is that if a molecule only has one chiral center, it's definitely a chiral molecule or a chiral compound. But if you have more than one chiral center in there, it could be not chiral anymore, right? Or known as achiral, right? If it has a plane of symmetry. So if you look at this guy here, we have trans 1,2-dimethyl cyclohexane. And this is definitely a chiral compound because it has 2 chiral centers here, but there's no real plane of symmetry here. But for cis 1,2-dimethyl cyclohexane, again, 2 chiral carbons right there, right? 2 chiral carbons right there. But there's a plane of symmetry right there. And now you can see that those are actually mirror images of each other. So they're not chiral, right? Oh, damn it. I did that again where the next slide explains what I just said, okay? So it's okay. We can review. The trans isomer is chiral, but the cis isomer is not. It's achiral, right? If the molecule has a plane of symmetry, it will be chiral. It will be achiral, right? The cis isomer has a plane of symmetry, which means it will have it will be superimposable on its mirror image and is not a chiral compound, which is what I just showed you in the previous slide, right? There's the mirror image right there, and it's the same on both sides. So if you have compounds like this, right, where they have multiple chiral centers but a plane of symmetry, they're called mesocompounds, okay? So another way to test if a compound is a mesocompound is to see if it's identical to its mirror image. You can draw the mirror image of the cis isomer and show that it can be superimposed on its mirror image. So by definition, when a compound is identical to its own mirror image, it's not chiral, it is achiral, right? Basically, just this slide just reiterates and restates, reminds you of what I just said in two slides ago. All right. If a compound has a plane of symmetry, it is achiral. Yes, we've already flogged that dead horse. Okay. But a compound that lacks a plane of symmetry, this is where it gets different, may still be an achiral compound. So if you look at this guy right here, that guy right there, I guess I should move my head out the way so you can see it better. There we go. That guy right there, that guy definitely doesn't have a plane of symmetry, right? Doesn't have a plane of symmetry. But the interesting thing, though, is that if you flip it, which is what that means, invert it, right? Inversion, about the center point of the molecule. What that means is flipping this guy. So this methyl group is at the bottom now. This one up here is at the bottom now. And then this methyl group here is at the top now. And you flip it, right? The molecule would still look the same, right? The molecule would still look the same. What that means then is that it's achiral because of inversion, because it's symmetrical about an axis, right? It's symmetrical about an axis because you can flip this right here. It's not a mirror plane of symmetry, right? But if you flip it, the methyl groups will still be at the top going towards you and at the bottom going into the piece of paper, right? So this is still achiral because it is symmetrical, right? Because of it can invert through a point through a axis of rotation. Okay. So in summary, right, the presence or absence of a the presence or absence of rotational symmetry is irrelevant to chirality, right? A compound that has a plane of symmetry is achiral. A compound without a plane of symmetry will usually be chiral, but there are exceptions, such as a compound with an inversion center, right? And that inversion center for this guy is right here. That's an inversion center. Okay? So let's talk a little bit more about mesocompounds. A compound with chiral centers but is achiral because of symmetry is called a mesocompound, which we already know. And these are all examples of mesocompounds, right? Here's your plane of symmetry there, plane of symmetry there, plane of symmetry there, right? You can still, mesocompounds are going to have less predicted stereoisomers than the 2 to the n formula that you can do with like general stereoisomers and chiral centers, right? Practice identifying mesocompounds with Skill Builder 5.7 on the Wiley Plus, just for you. And I forgot to bring myself back, so let me bring myself back. It makes me feel better when I can see myself in the lecture. I don't know if it makes you feel better, but it makes me feel better. Ooh, okay. Now we're going to talk about Fischer projections. So there are multiple ways of drawing molecules, right? And we already encountered Fischer projections before when we were talking about drawing sugars. So in a Fischer projection, right, if it's going up and down like that, then it means that that constituent is going into the back of the paper. If it's going horizontal, left to right like that, that means the constituent is coming out at you, okay? Coming out towards you, okay? Which is just a review because I've talked about this before when we were doing molecular representations. Was that like the third lecture? So, like I said before, sugars are the most common way we represent these kinds of Fischer projections. And the reason why is because sugars have multiple chiral centers, and just using a Fischer projection to represent a sugar makes it easier to see the chiral centers in a sugar, right? So, for example, this guy right here, 2 chiral centers. This guy right here, 3 chiral centers. This guy right here, 4 chiral centers, right? 4 chiral centers. We all know, and obviously they're chiral centers too, because this is, this constituent is an aldehyde right here. This constituent is an OH, is a hydrogen here. This constituent over here is a OH, alcohol, and this constituent over here is a carbon, right? And that's true of all of these. So they're all different constituents on the chiral center, on the chiral carbon. And so that's why they all have multiple chiral centers. Oops, I went backwards. There we go. So, using a Fischer projection, you can quickly assess the stereoisomer and relationships, stereoisomeric relationships, right? Because enantiomers are going to have the bromine substituents there on the same side, right? But mirror images of each other, right? Because remember that enantiomers are what? They are non-superimposable mirror images, okay? And then diastereomers, right here, are ones where the bromines are one side, and then on the other one, the bromines are on opposite sides. And those are the diastereomers. Practice assigning this. 5.8, Wiley Plus, just for you. Good luck. Whew, okay, and then, I think we're getting towards the end here, because this was a long one, and I apologize for that. Molecules can rotate about a single bond, right? We already knew that. So, recall that the Gauss rotational conformation, recall that the Gauss rotational conformation of butane, which is this right here. These are the Gauss conformations of butane, right? I've been talking so long that I'm like starting to stumble my words here. I apologize for that. And so realize that these conformations are chiral, and they are actually enantiomeric. But since there are conformations that can change, right, via bond rotation, butane itself is not a chiral compound. Okay, butane itself is not a chiral compound. Okay, the conformations can be chiral, right, and they actually are enantiomeric when they're in the Gauss. But remember, you're rotating around a single bond. And so when you're rotating around that single bond, right, that it's a fleeting thing. It's a temporary thing that they're chiral. So butane overall is not a chiral compound, right? Not a chiral compound. So that would be true of all bonds, all molecules that have single bonds and their Gauss are like seem chiral, right? Conformations seem chiral. But in the end, the molecule itself is not chiral. Okay? Because you can rotate around a single bond. So both of these chair conformations here, cis 1,2-dimethylcyclohexane, right, are possible. Okay? These chair conformations are chiral and are also enantiomeric. Okay? But when these conformations interconvert, and overall, this is an achiral compound, right? Because it can change its conformation. Okay? And now the methyl groups are both pointed downwards, and you have the internal plane of symmetry right there, and now you have a mirror image, right? Same thing there. And that's why just like the butane, this cyclohexane, this dimethyl cyclohexane, right? When in this conformation, these two conformations right here, right, these chair conformations, they are chiral and enantiomeric. But remember, it changes, okay? And it can interconvert so that overall the compound is not chiral or achiral because it has a plane of symmetry. Then we also have this guy here, BNAP, as they call it, BNAP. And I've never been able to say this word. Atropisomers. I feel like I'm supposed to say it really fast, like stereoisomer. Atropisomer, whatever. So atropisomers, they're stereoisomers that would be interchangeable through rotation of a sigma bond, but because the bond is unable to rotate, the different conformations conform and are stuck and not interchangeable. So in the instance of BMAP, right? BNAP, you have SBNAP and you have RBNAP. Okay? And generally, right, you could rotate around this single bond right here. Okay? You could rotate between that single bond right there and make it achiral, right? But the problem is that this right here, those are phenyl groups, right? pH is phenyl, and phenyl groups are huge because they're big benzene rings and they like to repel each other. And so naturally, the rotation can occur. And since it can occur, BMAP is chiral, right? As opposed to the previous one, right? Where these are chiral when they're in the chair conformations, but they can conform into other conformations that will make them have an internal plane of symmetry. In BNAP, right? Technically, it has a single bond, right? Like in methane, so it can rotate, right? And make it not chiral anymore, technically. But there are groups on it, like these phenyl groups right here, that make it impossible for it to rotate, to become symmetrical, right? And so that's why R and S BNAP are chiral and enantiomers of one another, right? So instead of having a chiral carbon as its source of chirality, its chirality is thus sourced from an axis of chirality. So you can have the chiral carbon be the chiral center, or you can have an axis of chirality too. The axis of chirality here is this bond, the single bond right here, that's supposed to be able to rotate, had it not been for those big phenyl groups, hanging out right there. But it can't. So that's why it has this axis of chirality. Okay? So that was a lot of stuff about chirality. I think this is the last slide. Oh, there's more. I'm sorry. This is a longer presentation than I thought it was. So there's more. There's allene now. Okay? This is allene right here. And compounds that possess two adjacent carbon double bonds, right? They may or may not be chiral depending on the substituents. Okay. If the two groups off of the allene, that carbon right there, are different, then they are definitely chiral. They're enantiomers of each other. Okay? They're enantiomers of each other. Okay. Because you can see here that there's a mirror image, but it's not superimposable, so they're definitely chiral. And the reason why they even show this as an example is because since it's two double bonds, right? Actually, I can show you by building it for you. What happened to my double bond one? Oh, I used it for the auction. Let me just build it for you real quick. That's why it's handy to have a molecular model kit around. Okay, here we go. 4 bonds, 2 carbons. Three carbons. And then that. Okay. And then we want a hydrogen on one side. And a hydrogen on the other side. Okay. And then we want methyl groups. All right. So here's allene built, right here. And as you can see, right, the drawing in itself of allene right there, the allene is just this part right here with R groups on it, right? It looks pretty symmetrical, right? But when you turn it, you can see that the bonds are perpendicular to each other from one carbon to the next, right? So that shows then that the p orbitals, right here, are actually perpendicular to each other, Okay. What that does then is it rotates the carbon, right, 90 degrees on one end, right? So now when you have actual R groups on it, substituents on it, right, a methyl group sticks up over here, but this methyl group sticks up over here, sticks out to the side, right? And so that's why this is now an enantiomer, right? Because if you were to put a mirror here, right, draw its mirror image on the other side, they would be non-superimposable, right? But they would still be mirror images. And that's why it's an enantiomer, okay? I think a lot of people, when they see this molecule, they think that the double bonds, those consecutive double bonds, are actually sitting like this, right? Where they're parallel to each other, right? Like this, right? Not flat like that. But that's not true, because remember that the position of the orbitals on the carbon are in tetrahedral shape, right? So you got two coming out to the side, but then the other two are actually perpendicular to each other. And that's why allene does that. And that's why it has chirality without chiral centers, right? Cool stuff. Ooh, oh yeah, forgot about this. We've got to get into some experimental stuff. So it actually turns out that it's really hard, right, to purify. It's really hard to purify enantiomers, right? And we spoke in the last lecture about how enantiomers of each other have very different pharmacological effects. Like, and I had said something about a drug that was causing birth defects. One of its, I can't remember which stereoisomer it was, but it was tholamide, right? I can't remember if it was the R or the S version that was causing the side effects of the birth defects. But a student, one of you guys, one of your classmates, posted a comment on YouTube and reminded me that it was tholamide, because during the lecture I could not remember what it was. Anyway, so that just shows you then that, having to separate out, these mixtures of these enantiomers, it's, racemic mixtures, very difficult to do, because generally, as you saw in lab, or as you're going to see in lab, like, we do separation based on physical properties of a molecule, right? So you can distill molecules, like when you distill alcohol, you can separate it from, the water from when you're using yeast to make beer or making, vodka or something, or in my case, Everclear. And water has a boiling point of like 100 degrees Celsius, and ethanol has a boiling point around 74 degrees Celsius. So you can literally separate it by boiling off the alcohol, leaving the water behind, and then collecting the alcohol in a different pot. And that's distillation, right? But that's based on physical property. You can also do recrystallization, right? And that's based on different solubilities, right? So those are all physical properties of molecules. And we depend on those physical properties to be able to separate our products from any waste and other stuff that we don't want in a reaction. But the problem with doing that kind of thing with enantiomers or racemic mixtures is that, remember, enantiomers have the same identical physical properties. So how do we do it, right? And obviously when they had tholamide, they didn't do a really good job, because people were getting birth defects. Babies were having birth defects from moms that were taking the tholamide. All right. So Pasteur here, and I think this was Louis Pasteur. Back in the Renaissance period, scientists were truly scientists. They weren't just biologists, chemists, or physicists, but they studied all kinds of sciences. And I guess at the same time, Louis Pasteur here, if this is Louis Pasteur, you can tell me in the comments if I'm wrong. But if this was Louis Pasteur, man, he was talking about doing pasteurization and microbial biology and all that stuff. All at the same time, he was trying to figure out how to separate out enantiomers. Now, that is a Renaissance man right there, right? We all wish we could be general. Sadly, we're so specialized now in the modern time. We're not like, general scientists anymore. But anyway, he performed the very first resolution or separation, right, of enantiomers, of a racemic mixture of tartaric acid salts. Okay? And so, interestingly enough, right, the different enantiomers of tartaric salts, of these tartaric salts, they actually had different shaped crystals. And so what he did was he went through and painstakingly, after recrystallization, used tweezers and separated each of the enantiomers by separating them manually using tweezers. Wow, right? That's rough right there. That's really rough. So we use the word resolution here, and resolution just means literally separation, right? The better the resolution you have, the better the ability you have to separate something out. Okay, and so while this worked for these two pairs of enantiomers, it generally doesn't work. So another method of doing this, of resolving, right, two different enantiomers or separating two different enantiomers is to use a chiral resolving reagent, chiral resolving agent, right? And so when you add a chiral resolving agent, and this chiral resolving agent reacts with each of the enantiomers, right? They will end up having, they will change the physical properties of each enantiomer, and then you can easily separate them based on one of their physical properties, right? One of the more common ways of doing it is actually using a method called affinity chromatography. So affinity chromatography is quite literally chromatography is called chromatography because of chroma, which means color, graphy because of graph. But back in the day, the first time anyone ever separated anything out, right? They used like dyes, and they made the dyes go through this glass column that had like a medium inside, sand, right? Silica gel, whatever. And then when they separated the dye apart, it resolved in all these different colors, and that's why they call it chromatography, right? And so, if you're using silica gel, that what we call the stationary phase, the silica gel, the solid stuff inside the glass tube, it's polar, right? It's a polar compound. And so when you add a mixture of things to that glass column that has silica gel in it with some kind of solvent in it, probably like ethanol or something like that, or no, maybe not ethanol, maybe ethyl acetate, something like that. Anyway, it doesn't matter what the solvent is. You pour it in there with the mixture, right? And it starts separating it out because each of the components of the mixture will interact with the silica gel differently. And molecules, right, or each component in those molecules, the more polar they are, the more they like to interact with the stationary phase or the silica gel. So it slows them down, right? Because they're interacting with the silica gel. But other molecules that are not quite as polar will pass through the column faster, right? And every molecule has a different polarity. And so silica gel is a good way of separating molecules out based on its polarity. Okay? And so that's a very common way of chromatography. Well, now this, though, is actually even more specific than using polarity because this is affinity chromatography. So here, instead of just using a generic silica gel, you'll use in the stationary phase, and we call it stationary phase because that stuff that's in the column, either the silica gel or the media that's for the affinity chromatography, it stays still, right? And the solvent that goes through it is moving. Excuse me. And so we call that the mobile phase. And then each one of the components that's in there is called the analyte, right? That we're trying to separate out. And so you can use some kind of different media instead of silica gel or something else, right? Sand or whatever, right? That has an affinity to your enantiomer that you want to resolve. Okay? And so when you pour in your mixture, your racemic mixture, right, into the column, the enantiomer that most interacts with your column of stuff will slow down, while the other enantiomer will flow out faster, and then you can easily separate them, right? So that's a very common way of doing, of resolving enantiomers or separating out enantiomers, right? And affinity chromatography is used in a lot of different things. I mean, I use affinity chromatography all the time in biochemistry to separate out like proteins that I use, I grow or synthesize. Couldn't remember the word synthesize. Yeah. So affinity chromatography is super helpful. You'll learn a lot more about chromatography methods. Don't worry about it so much here, but you'll learn a lot more about chromatography methods in Organic 2 when we get into spectroscopy and stuff like that. Which, by the way, I'm teaching Organic 2 in the fall at TCC, so some of you may be in that class. I don't know. Let me know. All right. Whew, okay, so turns out that having cis and trans isn't quite adequate, right, to differentiate two diastereomers that have different groups, right? So remember before we had cis and trans because on either side of the alkene's double bond or on the same side of the alkene's double bond, it was a methyl group. And the methyl group those are identical, right? But if you have two different groups, for example, here you have an amine and you have a fluorine on one side, and then on the other one you have an amine and a fluorine on opposite sides, you can't just use cis and trans, right? You can't just use cis and trans. So this is when we come in with the E and Z notation, right? So how do we do E and Z notation? In E and Z notation, we have to prioritize things again, okay? So step one, prioritize the group attached to the carbon-carbon bond based on atomic number. So here we have carbon up here, hydrogen here, right? Fluorine there, and nitrogen there. Fluorine is the highest priority because it has the highest molecular weight. So that's one. Nitrogen gets the second highest priority. Okay. Sorry, I said that wrong. Nitrogen gets the highest priority over here because it's got a higher atomic weight than hydrogen, right? So over here, fluorine is 1, carbon is 2. Over here, nitrogen is 1, and hydrogen is 2. Okay. So, unlike in the Kahn-Ingold pre-log system, you're not prioritizing all 4. You're prioritizing 2 at a time, and they are the 2 that are on the same side of each other of the double bond, right? On either side of the double bond. So, if the top priority groups are on the same side of the carbon-carbon double bond, then it is Z for zusammen, right? Which means together. If the top priority groups are on opposite side of the double bond, then it's E for integen, which is opposite, right? So notice here, fluorine won that priority from carbon, and nitrogen won the priority from hydrogen. So the two highest priority groups are on the same side. It's Z, right? And then E here for fluorine and nitrogen being on opposite sides, because there's the highest priority, right? So, practice with skill builder 8.2, drawing enantiomers on Wiley Plus. And that ends today's lecture. So there will be a quiz today, assigned today, quiz 5. Also, the stereoisomerism assignment will also be assigned today. Both are due by 7:59 a.m. tomorrow. That's June 11, 2021. Also, reminder, exam 2 is tomorrow, Friday, June 11th, 2021. And then, oh yes, don't forget that you have your caffeine lab today too. Excuse me. Don't forget that you have your caffeine lab today too, right? And that's due by the end of the day tomorrow as well. And then also remember that you have your lab midterm on Tuesday. Okay? Just a quick reminder, I'll be posting the quiz solutions in video form before the test, before the exam, so you can use those to study. Also, I think I said this before, but I'll say it again. One of your classmates asked me to actually make PDF versions of the of the assignments so that you could work the assignments. I didn't realize that the only thing that they showed you on the Blackboard after you get done with an assignment is just the question and what you got wrong and what you got right, but no answer choices. And though I want you to be able to answer the questions without the answer choices, I know how much you need to study. So, especially learning how to cross out the ones that are just impossible. So, I will post PDF version. I will begin posting PDF versions of each assignment for you to work on the piece of paper on a hard copy first, and then submit those to Blackboard, right? Using, you write your answers on the piece of paper, then you go to Blackboard, go into the assignment page, then put in your answers based on what you have on your piece of paper, right? And then that way, once you submit it and it's all said and done, you still have a copy of what you did before. Okay. All right. Good luck on the test tomorrow, and I do have office hours on Thursday, which is today, from 4 to 5. But I already have a student one of your classmates has already made an appointment for me during those office hours. So if you need to talk to me, make sure you talk to me either through email or on Teams. You can chat with me on Teams. Your best bet right now is probably going to be through email if you need to ask a specific question. You can also email me to try to make an appointment, but this close to the exam, I don't know if I can guarantee anything. But just make sure, if you have a question, make sure you either IM me over Teams or send me an email, right? Because I can just as easily answer a question for you over email. All right, good luck, and I'll talk to you guys next week, right, for the next lecture.